Today, as the title says, we're going to be talking about mapping the nano. I hope many of you were able to see my webinar last week for mapping in minutes. In that one, I covered a lot of the basics of spectral imaging and how it can help you solve materials problems. I will gloss over some of those basics because we have a lot to cover today in this webinar, and so let us begin. So first of all, why do you need to map on a nanoscale, or actually any scale? You could be looking for defects. You could be looking to see if a product was made the way it was supposed to be made. You could also be trying to figure out how your competitors are making their products, or you can look at how things are breaking when they're not supposed to and do a failure analysis. Of course, there's lots of applications. When you're really trying to get to the nanoscale, many applications aren't appropriate for that. You really have to pick it on a case-by-case basis. Many of the applications are in semiconductors and platings and optical coatings, and these can apply in many industries, including medical devices and many, many others. So it really needs to be evaluated on a case-by-case whether you need to map on the more macro scale or the nanoscale. So last week we talked about the sampling volume that EDS picks up when the electron beam hits the surface of a sample. So in my graphic on the right here, we have an electron beam coming in from the top. It hits the surface of, say, in this case, a piece of aluminum, and the electron deposits its energy in a random pattern throughout the material, and the scattering of those electrons give you this kind of teardrop-shaped region from which all the X-rays are going to be emitted, and it's those X-rays that we'll be measuring when we do the EDS, energy dispersive spectroscopy analysis, to figure out what elements are present. If you have a different material, then you could have a very different size analytical volume. For instance, if you see iron here, instead of being a scatter of up to, say, 10 microns worth of material, iron may only be 3 microns across. But for both of them, the majority of the information does come from the middlemost couple of microns. But when you're trying to map on the nano, you still want to see finer than a micron or a few microns in order to really determine what's going on that very small scale. So the problem with this beam spread is that it will tend to blur features that you're trying to look at on that nanoscale. If we look at my pictogram again, the reason, or the way rather, that we're going to get around this limitation is by making very thin samples. So if we look at the graphic on the left-hand side now, if you remove the bulk of the sample so that you no longer have all that material which contributes to the extraneous X-ray signal, you can see that the lateral distance from which the information can come is greatly reduced. And so when you get a piece down to half a micron thick or 500 nanometers, your lateral spread is around a micron. If you get down to just a tenth of a micron or only 100 nanometers thick, then your spot size can be measured down in the nanometers to tens of nanometers. And so that's obviously an improvement over this 10 micron volume from which you get data in the bulk when you're getting down to that very thin sample. So you really increase the spatial resolution by a factor of almost 100. And when you take data in this method, it's called scanning transmission electron microscopy, because the majority of the beam passes right through the sample and is transmitted as opposed to actually depositing its energy in the bulk. And so therefore, it doesn't contribute to the signal you're going to get. Only the electrons that deposit their energy in that thin little slice will give you signal. So how do you make these thin samples? Well, there are many different ways to make these thin samples, but the way that we do it here at Analytical Answers, for the most part, is to use focused ion beam milling. And that's a technique which uses a gallium ion beam to erode material in a very specific way to make very delicate cross sections. And this example here is a computer chip where the material in front of these metal lines was removed as well as in behind them, so you're left with a little brick of standing material, and you can target these cross-sections very, very carefully to the submicron level. And so that's the advantage that Fib has over most of the other TEM prep methods, is that it can be very, very site-specific when you're trying to look at a very small targeted feature, and we'll cover that when we go through the examples later. So the Fib process is a multi-step process. First you have to double-side section, which I showed in the previous page, where you remove a bulk of material from in front of and behind the region of interest. And then you use a microprobe in the vacuum system of the Fib to lift out the sample. And these images here were actually taken in the Fib during a process where a thin section was created. Then you take that little tiny sliver of material you freed from the surface and you attach it to a sample holding grid, and then you do some final thinning, and that's what's illustrated at the bottom of the screen on the right, where you have this little beam of material, and then in two select locations material has been removed away so that we get down to that very, very thin, roughly 1/10 of a micron thick layer that you're hoping to have the beam shoot through so that you have very, very small analytical volume. So I'm just going to come through an example of the Fib process. We're actually on the Hitachi S4800 SEM with Thermo EDS today, so the Fib is not live in this demonstration like the SEM is. So here we see a series of metal lines running on the surface of a semiconductor, and this line that terminates here actually on the left-hand side is a contact that leads down to a buried layer. And when we do the beginning of our sectioning, we can actually see that on the right. That's the picture from before. There's some fiducial marks that we burned in on the left and the right of the cross-section to mark the location of that contact, so that when we start cutting, we make sure that we hit the feature of interest. Again, it's a fraction of a micron. Seen from the side, here we can see that we have the two holes that we've dug out to free out the cross-section. And then on the right, you can see that the little tiny sliver of material, which is about 20 microns long at this point, and it's only about a micron thick, you can see that it's been undercut on three sides. You can also see the structure of interest, that contact right near the middle of the screen where the metal line is connecting to that buried metal line. That's going to be our target for the STEM analysis later. So that little tiny sliver, now seen from above, is connected to this small nano probe in the left pane, and it comes in from the lower right and attaches to the sliver, and then you cut that remaining material that was holding it to the bulk of the sample. You then drop the sample holder out of the way, and you're left with this sliver sitting on the end of the probe, and then you attach it to the TEM sample grid, as it's called, or half grid, which is typically used in the Fib. The grid is actually made out of copper, and you can sometimes see copper in the EDS spectra from the fact that some electrons scatter from the material that you're passing the beam through. And this is a function of the energy of your beam and also the proximity of the region of interest to the copper. So in many of these analyses, you'll see copper because of the grid that the very thin sample is mounted to. If copper is an element of interest, you would switch to grids of other materials that wouldn't interfere with what you were looking for. But that really depends on the specifics of your analysis. So now, again, this is after the samples have been finally thinned, and this is our video chip sample. We see two different regions that are going to be of interest, the contact and then a straight metal line adjacent to it. So now we are going to switch to the Sem Live View. And give me just a moment to focus the beam on the region of interest. I'll try and do this quickly so that you guys don't have to watch me focus the SEM for too long. So now we have that contact that we saw in my slide, and we can see several things about it. This is an image that's taken in transmission mode. So things that are higher in atomic number are darker because they tend to stop the beam. So we have a dark cup-shaped layer here, and there's also a dark one on top, but most of the other materials in the vicinity are very light in color. So we're going to just line up on the region that we're interested in taking data from, and then we will switch to the EDS software and begin acquisition. The first thing that's done is it captures an image, and this is very much analogous to what I covered in the mapping in minutes demonstration last week. So we capture this image so that we can overlay map data later, but equally importantly is that the software looks at this image periodically during the analysis, and it compares it to see if there's any drift in the sample as the analysis progresses. And so it actually performs a very important function to make sure that all the data registers on the features that it's supposed to. So now I'm going to begin the analysis. The beam is now going to be rastering over the field of view here at about 1 frame every 10 seconds. And we can start to see elements appear over on the right-hand side. And we can actually get a kind of a pretty good picture in just a few passes, which is really just a testament to how far along the hardware of the SEM and the analytical detector and the software, how far they've all come over the past few years and decades. So even though we can get a pretty good picture, like for instance, we could see that the titanium is what's associated with this dark layer at the bottom and along the top of the contact, it's not a very clear picture yet, and that's because we need to let the maps run longer. So this one's only been running for a minute, and again, we do have a fairly good picture of what's going on. But if we go back to my picture of what happens when the E-beam hits the sample, I will explain to you that we can't do mapping in minutes like we did last week. Last week we were able to get very, very high quality spectra extracted from maps that were acquired in just 2.5 minutes. The reason why you can't do that when you're doing thin samples for EDS is because all the signal that would have been generated in this volume here gets thrown away because it's no longer there. So because you're collecting signal from a much smaller volume, you have to let the maps run significantly longer. And how significantly depends on just what elements you're looking for, and also it depends on how sensitive you need the analysis to be. So this map has now been running for 2 minutes, and while the picture is not bad just from an eyeball's perspective when seen small, if you were to try and extract any quantitative information from this, it would be difficult. So because of that, I have actually collected the maps for these samples ahead of time. And the maps that I collected, I ran for a total of 15 minutes. So this is a map of that same feature that was acquired for exactly 15 minutes. And you can see that the data shows all the same information, but with just a much greater clarity. So again, we see the titanium maps precisely to excuse me for a second, this was a very dark layer when seen in transmission, but this is a backscatter image in the map that I have previously acquired. And so here, higher atomic numbers are brighter as opposed to darker. But still, looking at the position, we can see that the titanium is associated with the layer that runs across the bottom and top of the contact. And we can also see that the nitrogen is also associated with those layers. So what that indicates is that we have a titanium nitride barrier that's keeping these the metal layer in the middle, which is aluminum, from diffusing into the layer on the bottom, which is silicon. And that's a fairly standard semiconductor stack that you would see to have the titanium nitride barrier from aluminum diffusion. But again, what we're trying to talk about here is mapping the nano. So if we put a ruler on these layers that we're looking at here, we can see that this layer here that we've resolved with quite good detail is only 170 nanometers thick at the bottom. And if we look at the one on the top, we can see that the layer is only about 20 to 30 nanometers thick. So as I mentioned, we could improve on the spatial resolution of mapping by a factor of almost 100 by making these thin samples and doing the analysis in transmitted mode. One thing I want to do is, I see when I look at the silicon map, there seems to be a very faint hint of a layer of silicon actually between the titanium nitride and the aluminum that makes up the metal of the conductor. So I'm actually going to do an extracted line scan across these interfaces to understand what's going on there. And the way the line scan works is it averages data over the width of this arrow and plots the data as a function of distance along this line. And I'm just going to set the width of that to be a little bit thinner so that it's appropriate for the width of the feature we're trying to average over. And then recalculate that. And now on the right-hand side, upper right, we can see the line scan, and I can overlay each of these onto the arrow that's on the left. So here, when I overlay the titanium, we can see that there's a very, very large bump for the tinitride at the bottom, and a much smaller one, of course, for the one at the top, which makes perfect sense. If I look at the aluminum, it has a very strong signature throughout the entire middle of that part of the structure, because of course it's an aluminum metallization. But the thing that caught my eye before was the silicon, and now when I plot that, we can see a little bump in the silicon that's right along that interface there. And I want to investigate that further because I don't think I have quite enough resolution in this map to really see what I want to see. So what I'm going to do is move to the linear structure adjacent to this contact so that everything is going to be nice and parallel when I run this map, because that contact is actually a curved structure, and because of the geometry of it and the fact that it's not infinitely thin, it's just very thin, down around 100 nanometers, means that that geometry, that curved geometry is going to cause some geometrical blurring. So I'm going to go to 100,000x magnification and look at this linear structure here, which is analogous to the one we just looked at. So we should know what the major materials are that are present in this structure, but I want to get a better look at what that diffuse layer is right in between the aluminum and the tinitride. So now I'm going to switch back to the EDS software. And as before, I'm going to acquire a map. And again, we are at a 100,000x magnification, which gives us a field of view of 1 micron. And so when you consider what the expansion of the beam would do in a bulk material, where 1 micron is a completely mixed up blur, with these thin samples, we are able to get incredible high-resolution definition out of the information here. And again, it all comes down to doing very careful mapping on the thinned samples that have been prepared by the focused ion beam. So again, in just about 30 seconds, we already have a visual idea of what's going on. We want better quantitation, so we are going to run it longer than we would for our mapping in minutes. And so I do have the map saved ahead of time of this same region. But again, I just want to illustrate that you do get some feedback on this very, very quickly. And the advantage of that is if you found that you were not set up correctly for the right angle that you needed to come at the material from, or if it was just a bad region of the sample, you have very, very quick feedback on that. So it's not like you're committing to a very long experiment that might not yield the information you're looking for. So I'm going to stop that. And again, move back to the maps that I acquired before. And again, these were taken for 15 minutes, which is still quite quick in the grand scheme of things, in that you can complete an analysis in a very reasonable amount of time. So again, when we look at the extracted maps, and I'm going to convert these from raw counts to weight percent, which take into account chemical overlaps, we're going to get a much better picture of what's going on in all of these regions of the material at this much, much higher magnification, which you wouldn't really be able to resolve at all in the bulk. So as before, we saw our aluminum layer, which is the metal conductor in this chip. And then we see the Ti and the nitrogen, which make up the barrier that keeps the metallization from diffusing into the semiconductors below. I didn't really talk about some of the other elements we see here. We see oxygen because this is all encapsulated in silicon dioxide. And so when we plot the silicon map, we'll actually see that as well. We see silicon in the field all the way around the field of view, but then we also do see that little bright line that's running right through the middle of our screen here at the interface between the tinitride and the aluminum. Again, I'm going to use an extracted line scan to get much better sensitivity on this by averaging an entire width of pixels. And because we have a nice flat feature here, I'm going to increase the width of this substantially so that we can get a very, very nice data set. So now, when we plot our line scan, we could see again that nitrogen has a very strong peak right in the tinitride, which is where you'd expect it to be. And we also see that there is a very strong signature for the titanium, as you would expect, but you'll notice that they don't coincide perfectly. And there must be a reason for that. And so if we look at the oxygen plot, we can see that there's a very, very high concentration of oxygen at this bottom edge, which means that some of this titanium must have reacted with oxygen in addition to nitrogen to form a mixed oxynitride as opposed to just a pure nitride. But then you see the oxygen drops off at the top edge, so it's predominantly the bottom edge where you have that ti-oxynitride. Tinitride through the middle, and then if we plot the silicon, that's where we can see a very, very strong bump of the silicon right at the top of the titanium nitride layer. And so that confirms that this layer here is silicon rich, But it's not just silicon, because when we overlay the titanium, we can see that the titanium does extend into that region quite a bit. So that would indicate that we have a titanium silicide. One thing that is used in these aluminum metallizations up top here is that they actually do put silicon and a little bit of trace amount of copper in the metal to prevent diffusion of that material during device operation. So what it appears has happened in this case is that a lot of the silicon is diffused out of the aluminum and reacted with the titanium to form this silicide layer here at this interface. And again, just to illustrate the size of the layer we're talking about here, at its thickest points, it's only 50 nanometers, but in a very thin section over here, it's actually more like only 20. And so I want to see if I can see that. So I'm going to move my line scan to be centered on that very thin section. I'm going to narrow down the width of that so that we're only averaging data over that very, very narrow section just to see how far we can push our information here. And even though the signal to noise has dropped a bit because we're averaging a lot less data there is still a very, very clear silicon peak, even though we're averaging over this region that's only 20 nanometers thick. So again, that really shows just how far you can get extra data out of these thin samples in terms of improving your spatial resolution. So I've covered this example, again, the chip from the video card, which we just took off of an old computer and did a chemical de-encapsulation, which is something we do all the time to prepare samples for SEM inspection. And then I've covered this example, which was, although I went to higher magnification than this, was to look at that silicide layer that formed at the interface between the aluminum and the titanium nitride. My last example for the day is going to be what I've called an optical ink. And this is a color shifting ink where as you view it from different angles, you get to see a different color reflected back. And so this is something that's used in all sorts of places. You may have seen it on a driver's license or a building ID as some sort of security feature. It's actually used in consumer products when you're talking about high-end beauty products, for instance, where packaging is very important to making the brand stand out. And so here we have these little crystallites embedded in a polymer matrix. And this is, again, a Fib cross-section, focused ion beam cross-section that was prepared for this webinar. And we're going to target a few of these specific crystals to analyze and map. So going through the exact same procedures as with the previous sample, the piece was thinned, and then it was removed and attached to the grid, and then put into the SEM. And I do have this sample in the chamber as well. I think I don't need to show everybody the start of the maps again and just let them run for a second, because I think everyone's understood just how quickly you can get at least some information. But then I just wanted to at least show you the sample. So I showed this top down before, where there was two regions that had been thinned down on the sample. And that's exactly what we see here, is that there's two places where it's very bright because you have a lot more electron transmission because it's thin there. And in the thicker regions, everything is blurry because there's a lot more scattering of the electrons as they try and pass through the material, so you don't get that nice high-resolution view of the features of interest. So we can zoom in here and look at this crystal here. And this is, again, the same exact one that I showed in my slide. When setting up the map for this, it's very important to make sure that you line these up so that the beam is going parallel to these interfaces, because These crystals are randomly oriented in that polymer, and so when you're trying to take high quality, high resolution data, you need to make sure that geometrically things are lined up. Otherwise, you'll end up with blurring, not as a result of E-beam scatter, but just from the geometry. So if we go back to the EDS software, once again, I acquired a 15-minute map because I didn't want to make everybody sit through half a dozen 15-minute maps through the webinar. But we can still process the data as if I had just run it, something I talked about a little more in detail during my webinar last week is that these spectral images have all the data saved at the time of acquisition. So you have a full spectrum from every single point. So you can go in at any time you want and extract a spectrum from any region in this image and try and figure out what you have for a material, as well as change the types of maps that you are creating. You can go from just raw counts maps to net counts maps, which take into account the overlaps and the background that you would pick up. And you can also convert those to weight percent maps where you're actually using the sensitivities of each element in order to try and determine relative concentrations as opposed to just signal intensity. So again, if we process this map, I'm going to process it to weight percent because that corrects for overlaps and background, and then also takes into account the sensitivities of each of the elements. And again, this map took about 15 minutes. And so the preparation of both of these samples and doing all of the analytical work took just under a day. Doing the Fib cross-sections does take time because you have to double section the material, you do have to transfer it to the grid, and then final thinning. And that can take time depending on how difficult it is to reach the feature of interest. So now that we've processed our maps here, of course we have a very, very high carbon signature above and below the little crystal because we have the polymer matrix, and we also have a high oxygen concentration in those same regions for the same reason. We also see silicon in the map, and if you look at the image that I showed you in the slide, you can actually see little tiny dark blobs that are only about 100 nanometers across individually, although they're agglomerated in some cases to a half micron or so. And that's clearly a very, very fine silica filler that's mixed into the polymer matrix. And so we can see the signature from those as well. So now when we look at the maps, first of all, let me just point out that this entire feature that we're looking at here is only 1 micron thick. Just under, actually, 0.9. And so, again, we're seeing very, very small domains that you can't see when you do just standard bulk EDS analyses. They all would be blurred together in a bulk type analysis. And this layer, for instance, on the outside edge is only about 20 nanometers thick, and this layer at the inside is only about 50. So, what is this made out of? We see that we have fluorine, which takes up the bulk of those two thick layers across the middle of the crystal. We also have magnesium, which has a very strong signature across both of those middle stripes. Now, magnesium fluoride is a very, very common optical coating, and so it's not really a surprise that it makes an appearance here because its index of refraction and dispersion properties are going to be well known, and so it's going to be used in a lot of different applications such as this. In the middle, we have an aluminum layer, and again, that was only 50 nanometers thick, and you can see that the map shows it very, very clearly that that's right where it's located. And the presumption there would be that that's a reflective layer, so you act as it's a mirror, essentially, with, again, this magnesium fluoride on the surface to act as the optical medium. And of course, it's mirror imaged in structure, the whole crystal, in order to allow you to see it from both sides, because of course in the polymer matrix they're going to be randomly oriented. And then last but not least, those very, very thin 20-ish nanometer thick layers are associated very strongly with chromium, shown here in green now. And again, it follows the surfaces very, very closely, and you're able to see that the stack basically goes completely mirror imaged: chromium, magnesium fluoride, aluminum, and then the same thing on the other side. If we go to my full-size image, you can see a very, very slight shadow running down the middle of each magnesium fluoride layer. It's very, very subtle and hard to see, but if you take a look, you can see there's just a slight light band at basically 1/4 and 3/4 way through the entire thickness of this. And so I want to try and figure out what's causing that. So I'm going to go back to my old friend, the line scan, because I want to improve our sensitivity by averaging over a lot more data across the width of this. So I'm going to increase the width of my line scan extract to give me much higher signal to noise in the data I'm going to be looking at, and make sure we're nice and perpendicular to the interfaces of interest. And so now on the right-hand side, we can see our line scan for all the elements, and I'm going to individually overlay them on the line that's on the picture on the left. And so here we have, again, oxygen is associated with the polymer and the silicon in that polymer, the silicon dioxide. And there's a tiny little bump in the very middle of the layer stack, indicating that there's some association with the aluminum in there. It must have partially oxidized. And there's the aluminum layer itself, a very, very thin spike. And again, that was only 50 nanometers, which is, again, significantly thinner than you could normally pick out with just standard EDS on a bulk sample. And here's our two very narrow, let me change the color of that. Here's our very narrow chromium layers that are on the top and bottom of each of these crystals. But the ones I wanted to look at were the magnesium and the fluorine. And if we look right in the location where we had that change in color through the middle of each mag fluoride layer, you can see there's a little dip in the magnesium concentration and a little bump in the fluorine concentration. And so whether that was done intentionally or not, I can't really say. But it's very clear that we're able to detect something that's very, very subtle by using all the data available to us in this line scan extract in order to see that very, very subtle change in contrast is corresponding to a change in stoichiometry of that magnesium fluoride layer. This may indicate something they did on purpose, or it could be that when they did the deposition, they stopped it partway through and picked it up again as a two-step process, and then there's some non-uniformity in the deposition when it first initiates. But I was frankly pretty surprised we were able to see such a subtle feature. So that's my last example for the day. I would just like to emphasize that we'll be doing more upcoming webinars. You can also watch this webinar again or the webinar from last week, which has been recorded. You can watch our website for the dates of these upcoming webinars, incorporating WDS into the EDS analysis of metals and polymers. Wavelength dispersive spectroscopy, WDS, has advantages over EDS in that it has higher resolution and better sensitivity, so it can resolve peak overlaps that occur in EDS, and it can also increase your detection limits. So when you're looking at very low concentration dopants in a metal, or if you're looking at very low fill percents in a polymer, WDS can help you with both of those. It can also see low atomic number elements with greater sensitivity than EDS, all the way down to beryllium, with very good sensitivity. The next one's going to be benefits and applications of wet SEM imaging, and that's going to be on the Zeiss instrument we used last week, where you can look at fully hydrated samples, and you can actually watch transitions as they go from wet to dry and dry to wet through the introduction of water vapor into the chamber. And then we're also going to have a webinar on correlative optical and electron microscopy, showing how having high-quality optical images and SEM images of the same regions of interest can help you decipher what you're trying to understand about a particular failure analysis or reverse engineering project. And again, those dates have yet to be determined. So I'd like to say thank you for your attention today. I'll take any questions, or you can send questions to answers@analyticalanswersinc.com. And for those of you who are wondering, those little crystals that you saw in cross-section just a few slides back with magnesium fluoride, you may have seen them before. If you've ever looked at the reflective 20 on a $20 bill, if you come in at high magnification, this shininess is resolved to be all these little tiny flakes in there, and every one of those little flakes is one of those double-sided magnesium fluoride, aluminum, chromium stacks on all of our currency. And so with that, we'll see if there's any questions. And unfortunately, there's no questions.
Or fortunately.
Anyway, if you don't have any right now, please feel free to send them along to the web address on your screen, or there's another address that's listed in the link that you received, in the email you received for the webinar. With that, I'll say thank you very much for listening, and I'll turn this back over to Christina for just a few moments. And thank you again.
Thanks, Ed, for that very informative webinar. Thanks, Ed, for that very informative webinar. I think we will keep it open for a few minutes to see if anybody has any questions. Please feel free to ask. There's no such thing as a dumb question. There's no such thing as too complicated a question. We will get you your answer. So we are going to be here till like 12:50. If you do have any questions, and again, if you do not, we want to let you know to please tune in to the next webinar. We have one coming up in June. In addition to that, this recording is going to be sent out to everybody who participated, who was registered, as well as the recording for the previous webinar. So if you have questions at that time, please feel free to email them to answers@analyticalanswersinc.com. So it looks like we don't have any further questions right now. So with that, we want to thank everybody for taking part. And let you know that the recording will be available to you in an email to follow. Take care, everybody, and have a great rest of the afternoon. Well, it looks like you